so normally we should start on today's the overall the whole section. But before we start, I just remind our speakers, if you want the remaining time 15 minutes and 3 minutes left, our system will give a sign, and this means that you almost need to stop because you usually left some time for the question and answer question. This is also part of the evaluation. Okay, usually give time. Okay, so now let's start our first talk. The first talk will give by Jian Zhanghe from Tsinghua University. Yeah, his title is the photometric redshift nose ecliptic wide field based on deep optical survey using the hypersplenal tank. Okay, please start.
Thank you. Good afternoon, I'm Simon from National Tsinghua University, and I'm a second-year master student. My supervisor is Professor Tomosu Goto. Today I'm going to tell you a story about Akari, HSC, and Pelosi. So once upon a time, there's a telescope which is called Akari. It is an infrared telescope. And Akari, it has a very unique feature, which is it has continuous night band photometry in infrared to mid-infrared wavelengths. So this is Akari. And you can see that from this filter response plotting, there's no single gap in Akari bands. Compared with other well-known infrared telescopes like Spitzer or WISE, there are gaps in between the bands. So technically, Akari can detect those sources which are missed by Spitzer or WISE due to these gaps. So in 2012, one of our collaborators, Dr. Songjin Kim, he published a catalog paper about Akari data on the non-ecliptic or wide survey. And later, I will just call this NEP. So this slide, I will show you the coverage of our data on the NEP wide field. You can see that the great small circle represents the NEP deep field, and the larger green one represents the NEP wide field. And the red rectangle represents the CFHT megacam optical data, and the blue one represents the Micronic optical data. So you can see that for megacam optical data, it only fully covers the NEP deep field, but not the larger green NEP wide field. So we don't have enough deep optical data for our NEP wide field. So, but fortunately, in 2014, our beloved Professor Goto-san, he wrote a proposal to Subaru HSC survey to ask for observation time on our Akari NEP wide field. So eventually, we finally got the deep optical data on our field, which is pretty amazing. And just in case you don't know how amazing this is, I will show you a metaphor. So I don't know how many of you know this. So this is a very famous Japanese manga which is called Dragon Ball. So in Dragon Ball, there's one scene that two of the characters will do fusion, which is merged together to become a very powerful superhuman. So imagine in our data, which is Akari data and also HSC data, they try to merge together and become a very powerful band merge catalog. And Dr. Songjin Kim, he thinks this catalog is not powerful enough, so he even merged more telescopes data into our band merge catalog, like Spitzer, WISE, Herschel, CRT, Micronic, and KPNO. He merged even more data to our band merge catalog to make it more powerful. So this shows our NEP wide field region. The red one is the NEP wide field region, the coverage of. And the large cyan circles are the deep optical data from HSC. So this red circle is actually 5.4 degrees square large, compared with this small little guy here, which is the Changjiang Deep Field South, which is pretty big. And just let you know how deep our HSC data is. For HSC G-band is around 27 magnitude, compared with megacam G-band is 25.5 magnitude. So it's pretty deep. And don't even mention Micronic optical data. So my job was to estimate photo C for this red region. And just in case you don't know what is photo C, I will tell you the story. So in our data, there are two kinds of redshift, which is spectroscopic redshift, and in short is spec C, and photometric redshift, in short photo C. So for SPECSY, it's basically finding redshift based on features in spectrum. And it's very accurate, but time, money consuming. And for PhotoC, it's basically estimating redshift based on its photometric data alone. And in compared with SPECSY, it is less accurate, but much faster and less expensive. Many current and future surveys only deliver photometric data, and also spectrum of phase gas is hard to obtain, just like our phase mass nowadays. And therefore, PhotoC is a really efficient and powerful way to get redshift information and do further research. So this shows our statistics of our band merge catalog. So this is merged by Songjin Kim, and he will publish a catalog paper later. And sources in total is around 92,000 sources, and 2,000 of them with SPECSY. And the code I used was called LUFA. It's basically a SED fitting code algorithm. And the first question comes to us is, how many filters bands do we need to compute our PhotoC? So my answer is as many filters as possible. So here I show you different filter response from different telescope filters. You can see that even is so-called either I-band or HAC I-band or CVHC I-band, they are all called I-band, but they are slightly different in effective wavelength. So in order to construct a more comprehensive SCD, we need to have as many as possible. Moreover, there are some features like Baumann break in low redshifts. So U-band data is really important. So finally, we pick like 25 bands from our band merge catalog from Midnight optical data to WISE-12. And here I want to define some symbols in our plotting. So the first one will be N-gal, which is the number of included galaxies. The next one is eta, which is the outlier fraction. And outlier fraction are defined as delta C divided by 1 plus SPECSY, which is larger than 0.15 or smaller than minus 0.15. And the next one is sigma, which is PhotoC deviation, and it is normalized median absolute deviation. It is divided by this formula. And except for the N-gal, for eta and sigma, basically smaller the value, the better. So the first thing I did was to compare the template models to see which template model gives the best performance. So this time I fixed the filter combination as the 25 bands from Midnight to WISE-12. So here I compare 6 different kinds of template models from Cosmos to CWW. So you can see that Cosmos gives us the best results based on its outlier fraction and sigma, which is 16.3% in outlier fraction and 0.058 in the PhotoC deviation. So the next thing I did was to compare different filter combinations. And this time I fixed the galaxy template as Cosmos. So here I compare 11 different kinds of setup. So you can see that for setup E, it actually gives the best performance, which is the smallest outlier fraction and the smallest PhotoC deviation. And setup E is actually from Midnight to WISE-12. But it's only 24 bands because Flamingo J, if I exclude Flamingo J data, it becomes better. So here I conclude the best setup I had was Cosmos as SED templates and Midnight to WISE-12 as the filter combination, which gives us outlier fraction of 9.3% and 0.049 for PhotoC deviation. And this is the PhotoC plotting. Here I include like 1,854 galaxies, and it gives us 9.27% outlier fraction and 0.0493 PhotoC deviation. And the final thing I need to do was to separate star and galaxy in our PhotoC catalog. So I try to use the chi-square in our code, the chi-square calculated by our LUFA, and the stellar template I used was those. So basically there are 2 values I'm comparing, which is the chi-square gal and chi-square star. So chi-square gal is basically the minimum chi-square value when it's fitted to the galaxy template, and chi-square star is the minimum chi-square value when it's fitted to the stellar template. So when chi-square gal is larger than chi-square star, it's possible star candidates in our case. Vice versa, it would be galaxy template. It would be possible galaxies. So here I plot the color diagnostics to check if our star-galaxy separation is good enough. So you can see that there are 3 different kinds of colors here, which is the red one is galaxy, which is with C larger than 1, and the black one is galaxy with C smaller than 1, and the green one is dark candidates. You can see that there are 3, obviously there are 3 trends that shows these 3 kinds of things. And actually this is consistent with our blue dots, which is a spectroscopically confirmed galaxies. So it means our star-galaxy separation is quite good. And here I show the histogram for our photo C. So the dash 1, the histogram is actually before excluding stars from our photo C catalog. So after excluding those stars, you can see that the gray histogram, it becomes more natural. And the blue ones, which shows the spec C histogram. And I will try to compare our results to the previous work done by other people in the same NEP field. But this time at that time they tried to do the photo C on the NEP deep field. So you can see that for the same redshift range, our results outperform their results, which is 0.049 for our result and 0.1 for their results. And for outlier fraction, our result is 9.3%, which is around 20% better than them. And we have even more data than them. And one point I want to point out is that in their case, they are only using the Akari data. So this emphasizes how important deep optical HAC data is in our case. So the final question comes to us is that you may ask me, Simon, what are you going to do with this photo C? So I'm telling you that actually there are some people in our group doing the further research using my photo C. And actually it's very important in their work. So for example, one et al. In preparation, she is doing AGN contribution to total infrared luminosity region NEP. And Huang et al., he is trying to find clusters in NEP by using my photo C. And Santos et al., he is trying to do AGN contribution to local density relation in NEP. And for Wang et al., I will show you how important photo C is in her work. So you can see that for this blue one, if there is only spec C data, she only have like 400 sources. But if she include my photo C sample, it become like 1,600 sources. So it becomes more sources, which is it means more meaningful research being done. And for Huang et al., he's trying to find clusters in NEP. So if we only use spec C data, there are only 2,000 spec C data, which is very small, which is nearly impossible to find cluster. If he can use photo C, it will be very, very powerful to find clusters. So in other words, you can say that I'm actually controlling whether they can graduate or not. So my photo C is very important, really. So this is my summary, and I will take questions. Thank you.
Any questions?
So in your work, for nearby galaxies, the galaxy may be resolved with respect to the telescope resolution. For example, Akari, remember for bands lower than 25 microns, aperture size could be smaller than the size of galaxy in a nearby universe. So you may not, your aperture may not capture the entire galaxy flux. So in this case, did you take into this account the different aperture size in different bands? Because if you want to do a photo Z, I guess you need to use a total galaxy flux for light. Did you account for this effect? Do you know what I want to ask?
Yeah, I understand. But actually, I'm only using Akari N2 to N4, which is smaller than 4 micron. So I guess
smaller than 4 micron.
Yeah, I'm not using the 25 micron bands for calculating.
But if you use smaller, shorter wavelength, your aperture is your aperture smaller? Aperture size of the telescope. What's the aperture size of Akari?
The aperture size of Akari is about. Sorry, I forgot about this.
Okay.
I can tell you later.
questions or?
Second. So, how even is the depth across the field? Because you combine many different sources of photometry here, you know, from different pointings of different instruments. So I imagine you have quite some variation in depth, you know, chip caps and all this kind of thing. Does that impact on the photo Z estimation? You know, so some galaxies may be detected in one region in one band, but not detected in another region in another band.
Yes.
Yeah. Is that?
So in this MH catalog, I think our focus is Akari data. So it's like a infrared selected galaxies we are focusing on.
So do you require that a galaxy is detected in all bands before you apply them?
We require it should be detected in the Akari bands.
Okay.
Yes.
So if no question, let's move to the next speaker.